Okay, ladies and gentlemen, today we are going to solve some more problems about open systems, and it feels like we've been doing this for quite some time, and we have been, and we will be continue to do it with this in-person and online version here. We're just going through a lot of problems with this material. I'm considering on Wednesday, which we should go through more of this material, just going back to closed systems and refreshing some closed system stuff. I'll let you know what I decide on that later on. But this is the last material for the exam, which is a week from today. And I'll be getting up the practice exams and all that stuff today. I'm getting that ready for you. So today I have two problems to do, and the first problem I picked is one of the problems that I assigned on an exam in 2017, which students just hated, and I ended up hating for many reasons, and I'll talk to you about why I hated it, and we'll go over it together. But it's in premise pretty straightforward, but then there becomes a lot of questions you have to ask yourself that kind of complicates matters here. So here we go. We're going to have a flow coming in here of steam. So this is state one, we're going to have steam coming in. And it can branch and it can go into two places. The top one, it can go into a turbine, and then we're going to know this state over here is state 3. Or the bottom, it can go through a valve or a throttle, and this is going to be state 2. And this can all come back and get mixed up in a mixing chamber. And it's going to go out here at state 4. And here's the information that you are given about each of these states. State 1 is going to be a pressure of 500 psi, a temperature of 600 degrees Fahrenheit, and a mass flow rate is equal to 30 pounds per second. State 2, all we know is that the pressure of 2 is equal to 180 psi. State 3, we know that the pressure at 3 is equal to 180 psi, and the enthalpy of 3 is equal to 1200.5 BTUs per pound. And finally, we know state 4. State 4, the pressure of 4 is equal to 180 psi. Temperature 4 is equal to 400 degrees Fahrenheit. So that's what we know about this. And we want to find two things. We want to find the power that the turbine produces, and we want to find out what was the mass flow rate through the turbine and the mass flow rate through the valve. So this, let me make sure that we understand this is a valve. So this is a real typical problem that you're going to have, or you're going to have a situation like this in a power plant, where the turbine, sometimes you don't want to run the full load of steam into the turbine. You're going to bypass it with a valve. And so if we close this valve completely, all the flow coming in is going to go to the turbine and produce power. But on a hot summer day, when you have a lot of air conditioners going, you're going to want to close the valve and get all the power out. But on a day like today, when you're maybe not running as many air conditioners, you may not have to run the same amount of steam out, so we might just throttle it down by opening up this valve and letting some of the steam go into the turbine, but others are going around and go back into the mixing chamber and come back together. So this mixing chamber, all it is just a box where all that steam comes together, and you know that the steam all comes together at the same pressure. Okay, that mixing chamber all has the same pressures coming into it. That's important. So we want to find out, in this situation with these states, what is going to be the power that the turbine is producing, and we have to also find out what the mass flow rate is for the turbine and the mass flow rate is for the valve. Now, this is not a simple situation where the steam goes to this junction here. We'll call this junction right here, we'll call this A. It doesn't come into A and just say, okay, half of you are going to go north and half of you are going to go south. That doesn't happen. It depends upon the situation that we are deriving to figure out what happens. So the first most common thing that happened is students just said, hey, half it's going up top, half it's going below. We can't determine that, okay? So we have some questions. If we don't know how much is going through the turbine and we don't know how much is going through the valve, well then how can we find out what the power to the turbine is? Because I want to make my control volume equal to the turbine. And if I just go through it into my head, there are two unknowns in that energy equation. The first unknown is the mass flow rate. The second unknown is how much power it's producing. I can't solve that. So I need to think that's probably not my best system. Okay, so you have to think about what is a better system to look at than that system. And so you start with the smallest system and see if that works, and if not, you have to make the system bigger and bigger and bigger. Or you have to go to create another system to find that information. Okay, so I might go down here to the valve and I might say, well, I want to figure out if I make the valve my system, can I find out how much mass is going through the valve? Well, remember, a valve is the same as a throttle. Okay, the valve and a throttle are the same thing. So we know that the enthalpy in equals the enthalpy out, but that doesn't tell us anything about the mass flow rate. So if we look at this a little bit further, the control volume that we need to create is actually going to be this entire system. This entire thing is going to be the control volume. Because in this control volume, we know what's coming in, and we know the mass flow rate coming in. We know what's coming in, the mass flow rate's coming in, and we know that that same mass flow rate that are going to join back together is going to be coming out, and we can set the state going out. And then we have, inside the system, we have the power for the turbine. The power for the turbine is going to be coming out here, and this is going to be our W dot. Now, this is another thing that caused a lot of grief here, because I drew my turbine differently than I normally do. We normally draw the turbine, when I draw the picture, I draw the turbine looks like this. This is coming in at 1 and coming out at 2, and then we have a shaft coming out here that is going to be my power. Okay, I didn't do that here. I just said here is coming in and here is going out, and we have to understand there's a shaft coming out here that's producing some sort of power. The other question students say is, well, if I made this whole thing my system, isn't the power inside of my system? Well, no, the power is going to have to somehow, you're powering something. It's going to be extended out past this. It's going to go and connect to a generator or something of that nature. So it's coming out of here. So in the way that I drew this picture on the test, it caused a lot of trouble. It caused a lot of trouble in that test. It caused a lot of trouble on my T-valves. It caused a lot of trouble. I heard about this problem for a long time, okay? And it's one of those things when I drew it up, I didn't think about how you would see it and the complications of the matter, okay? But I want you to be able to tell the story here. Steam is having a choice whether to go through the turbine or go through the valve. Depending on how much I close the valve, it depends on how much steam goes through there. That turbine is going to be spinning. It's going to be spinning. And then that's going to produce some power. That power is going to go someplace else. It's going to go outside of, far away. So this control volume is a proper control volume to do. Okay, so that's what we're going to use to find the answer. And that was very difficult for many students. And we had to, and I probably was pushing them a little bit too far on this exam with this problem, and so I had to grade it. I had to kind of put in a little curve in the grading when I was working with it. So let's answer the first question now with our big control volume. I want to find the power for the turbine, and I want to say that the CV, the control volume, is my entire system. Okay, and if that's the case, I'm going to write my energy equation. dE dt is equal to Q dot minus W dot plus the summation of my mass flow rates in times my enthalpy in, plus my kinetic energy in, plus my potential energy in, minus the summation of my mass flow rate exiting times my enthalpy exiting, plus my kinetic energy exiting, plus my potential energy exiting. Okay, now, I didn't tell you in this problem, when I set it up here, anything about whether this is running a steady state or not. But I also didn't tell you anything about how it's changing with time. I didn't say it's ramping up to this value, it's going up to 600 degrees Fahrenheit, or it's coming down from that. So in the absence of that information, I'm going to assume it's steady state. And here's the thing, on the exam that you're going to have next week, they're going to have 2 closed system problems and 2 open system problems, and both of those open system problems are going to be steady state. I promise you. Now, Wednesday and Friday, we're going to be talking about non-steady state problems. That is not on this exam. That is on exam 3. So the 2 problems that you're going to have are going to be the energy problems, the problems that deal with the first law are going to be steady state. Okay, but you can also recognize it. You can also recognize it without the absence of that information, it's steady state. Now, the transient problems that we're going to deal with are going to be very easy to denote because they're going to be basically tanks that are going to have exits but no entrance, or entrances but no exits. Okay, so you're either going to be emptying a tank, the properties are changing with time, or you're going to be filling a tank, the property is changing with time. That's the typical one we're dealing with. Systems like this, steady state. Okay, so here we go, steady state. We are also not given any information about heat transfer. So we are going to go back to our most simple assumptions that the heat coming out of the turbine, there's no heat coming out of that turbine in the mixing chamber or the valve, that they are adiabatic or are well insulated. There's nothing in the problem statement or that I've told you that indicates that there's anything going on there. So we're going to go back to our simplest assumption is that, hey, this is adiabatic. Okay, so that goes away. There is going to be power coming out of the turbine, but the kinetic and potential energy effects, as they normally do, except for in nozzles and diffusers, goes to 0. Okay, so we have, this is going to be our system. Now, we write this as 0 is equal to minus W dot plus, we know here coming in and out that the mass flow rate of 1 is the same as the mass flow rate of 4. I can just logically go through that in my mind and say the mass flow rate times H1 minus H4. And that will give me that the power is going to be equal to the m dot times H1 minus H4. So now just by, we're not looking directly at the turbine, but we can find out how much power we have going on here. Okay, so m dot. M dot is going to be equal to 30 pounds per second. Okay. Now, I'm going to look at both properties. I'm going to look up the properties, and I'm going to then close out the document camera so it doesn't bother everybody. We know we're dealing with steam here. We're dealing with English units. And so we need to go back to our table A2. And we're going to go look in our, I'm going to go look into the PSI, that table. And I'm going to look for 500 PSI and 180 PSI. So 500 PSI, I know that I saturate at 467.13 degrees Fahrenheit. I'm at 600. That means I am a gas, a vapor. At 180 PSI, I saturate at 373.13 degrees Fahrenheit. I'm at 400, so I am a vapor. I always check to start with. You don't have to check. I'm checking just to make sure that, you know, I'm where I need to be. You could go directly and say, I know this is steam, and go directly into the steam and find the values. So I'm going to find the value for 180. So at 180 and 400, my enthalpy is going to be 1214.4. And for 500 PSI and 600, 500 PSI and 600, that value is going to be 1298.3. Okay, those are the values I'm going to use. Again, you could go directly there and I'd be 100% okay with it. I don't need you to go through a specific pattern. In fact, I don't need you to write down this energy equation and cancel things off if you don't want to. If you see it directly and can just write down the final equation, go for it. But I will have partial credit inside of there, so if you make a big mistake and I can't see what you did, you know, you have the risk of maybe losing a few more points. But you can save yourself a lot of time. Okay, so what I find for H1, make sure I'm back on where I need to be. H1 is 129, or H1 is 1298.3 minus H4 was 1214.4. Kind of hard to remember this. I'm looking at my notes because I'm trying to get off the camera so I won't keep it up there for everybody at home. BTU per pound. Okay, this answer is going to give me units of BTUs per second. Let's just say I'm looking for horsepower here, which I often am. I'm usually looking for kilowatts or megawatts in SI units and in BTUs. Sorry, in horsepower for English units. So the conversion there is going to be there's 3,600 seconds in 1 hour, and then I know that there are 45 BTUs per hour in 1 horsepower. And so now I can go through here and run through my values. 30 times 1,298.3 minus 1,214.4. I take that times 3,600 divided by 2545. And I get that this is going to be a 3,560.4 horsepower turbine. Okay, that's good. That's our value. We've answered part A. Now, for part B, we need to figure out how much mass flow rate that turbine produces. And now, if we look at that turbine as our control volume, now we have one of those 2 pieces of information that's missing. We know the mass flow rate. Or sorry, we know the power. We can find the mass flow rate. So let's use this as my second control volume, that orange control volume, and let's say here, B, the control volume is my turbine. And I'm going to go ahead and write out the whole equation, dE dt is equal to Q dot minus W dot plus the summation of my mass flow rate N, enthalpy N, kinetic energy N, potential energy N, mass flow rate exiting, enthalpy exiting, kinetic energy exiting, and potential energy exiting. And I'm going to make all of my assumptions here that we've made already in part A. But at steady state, our turbine is going to be adiabatic, and the kinetic and potential energy effects are going to be negligible. And so I will get that my power from my turbine is going to be equal to the mass flow rate through the turbine times H1, or I should say Hn minus H exiting. Okay, I'll say that right now. Because here's the question. We know some information about the enthalpy exiting. We know the state 3, we can set the state 3, it's 180. They gave us the enthalpy for state 3. But the question is about the entering state. And we know what's at 1, but we also know it branches up here and branches down. And so there's a possibility that the state may change when this branch happens. But I didn't give you enough information to work on that. So what I wanted you to do when you're solving this problem is to assume that the state 1 is the same up here as state maybe 1A. I wanted you to assume that this state 1 and state 1A were the same. And that was a little bit, that was an assumption. That was another additional assumption that some people made and some people didn't make. Some people tried to find out what was happening there and got into some weeds, and it caused some issues. But that's what I want you to do. I wanted you to do that. This is where you needed to go. Okay, so we know the mass flow rate. We're looking for the mass flow rate, so let's solve for it. Mass flow rate of the turbine is going to be equal to the power of the turbine divided by H1 minus H3. And we know the power was equal to 3,560.4 horsepower. And we're going to divide by H1, which I'm going to use my same H1 as I had up here, 1298.3. And then my H3 they gave to me in the problem statement was 1200.5, and this was in BTUs per pound. Okay, so I'm going to have to convert my horsepower back out here, or I could have had an intermediate step up here where I calculated BTUs per second. So I know that 1 horsepower is 2545 BTUs per hour, and I know that in 1 hour there is 3,600 seconds. Okay, always checking my units. Horsepower goes away, hours goes away, BTUs goes away, and I'm going to have pounds per second, which is what I need. And if I do this, I find that to create that power with that property, I get 25.74 pounds per second must go through that turbine. Must go through that turbine. So that's my mass flow rate of my turbine. That tells me that the mass flow rate of my throttle or my valve is going to be 30 minus 25.74, or 4.26 pounds per second. Okay, those are my answers there. Now, my philosophy in thermo is that the right answer is worth some points, but it's not everything. It's how you go about solving it, your thought process through it. So I looked at my notes here and my grading notes that I have for this, and I decided I'm gonna think about how students are thinking through this problem more than the points I give everything. 10 points for part A and 10 points for part B or whatever. I'm looking to see, how did you think through? What assumptions did you make? How did you communicate your knowledge to me? So if you get into a situation like this, I hope I never assign a problem like this on the tests, just to be quite honest. But if I happen to give you something that's clear to me but not clear to you, first thing you do is you ask a proctor for some help. Can you come and talk to me, see if I can't understand what Wanklyn is trying to ask me? And the second thing you do, if that still isn't clear, is you just dump in your information onto the page and you explain to me what you know. Okay? Here's some assumptions I'm making. Here's some things like that. I might count you off on that. But you have things documented on the paper that we can come back together and say, hey, I think you gave me a 12 out of 25 on this page. I think I showed more. And I wrote it down here. Look at this stuff. Look at this, X, Y, Z. I do it all the time. I've done it multiple times. I said, you know what, you're right. Here, I'm going to give you some points back for that. Your job is to show me. So if I get lost in when I'm just trying to grade real fast to get through things and count you off, we can always talk about that. So please use the paper as a love letter for thermo, okay? And express that love in writing. Any questions about this one? Disaster. This is not the worst problem I've ever given. I did give a problem on an exam that broke the laws of thermodynamics. And I didn't figure it out until in the middle of the exam. And you know what I did? I made the problem so that there was no interpolation. It had a whole bunch of interpolation on it when I tried. So I thought, I'm going to fix it so there's no interpolation. So I fixed it so there was no interpolation. And then I broke the laws of thermodynamics. So people started asking me questions during the exam. I went up and asked them questions. Why are they asking me these questions? And then I realized that I messed up. And then this cold sweat came through me. And I had 3 different rooms. I had to call a different room and say, hey, get them on the horn. This is what's going on. This problem broke the laws of thermodynamics. I just want to see your methods. I made it on Reddit because of that. I made it on Reddit. I gave everybody a certificate of completion for my exam, and they posted it on Reddit. I was famous for 15 minutes. Yes?
I did have a question in calculating
Yep.
You're taking 30 pounds per second because that's what you have for
Coming in.
the first part.
Yes.
So you wouldn't have the mass flow rate of any of the other numbers for that one, right? Because it's not going in.
So yeah, I just know this mass flow rate is coming in here at 1. I only know that's at 1. When it branches here, I don't know how much of it goes this way, and I don't know how much of it goes this way. What helped me figure out how much of it goes to the top is I knew how much power And because I knew the states going in, I knew that this much mass flow rate would have to be going to create that power. Okay? Now, let's talk about this valve here. What do we know about a valve, which is another word for a throttle? What do we know about those? When we see those, what can we say? The enthalpy remains the same before and after. Okay, the enthalpy remains the same before and after. So if I ask you to analyze this mixing chamber, now we know the mass flow rate coming in, and we know the enthalpy coming in. We know the mass flow rate coming in here, we know the enthalpy going in, and we know the mass flow rate going out and the enthalpy going out. We could make a calculation at that mixing chamber based upon that, because these are all coming together, being dumped into one container. Okay, let's do our next problem here. And the next problem is an air conditioner. And so here I'm going to draw this two big boxes up here, box here, and then a box down here. And I'm going to have a different way of drawing a valve. Okay. So here's my picture, and let me start labeling some stuff. This thing here is a compressor. I'm drawing it as a circle, not as our typical compressor, but it's still the same idea, just drawing it with a little different shape. This over here is an expansion valve. Okay. The top is going to be a condenser. The bottom is going to be an evaporator. Okay, and I'm going to label states here. 1, 2, 3, and 4. And I'm going to say the inside of this pipe is going to be refrigerant 22. R22 is going to be flowing through this thing. And I'm going to tell you that this compressor, I'm going to need to power it with 200 BTUs per minute. Okay, that's how much power I must provide to that compressor. And so let's take a journey and see if we can follow the R22 here. And I'm going to tell you what's happening at state 1. State 1, it's going to be a saturated vapor. And the pressure at 1 is going to be 120 psi. And then it's going to go through that compressor. And so it's going to compress it. And state 2, the pressure at state 2 is going to be higher, 225 psi. I'm going to tell you the enthalpy at 2 is going to be equal to 130 BTUs per pound. Now, this is going to be a hot vapor, and the condenser is going to do exactly what it says. It's going to condense that vapor into a liquid, and it'll go to state 3. State 3, we know that the pressure at 3, there's no pressure drop, which is 225 psi, and the temperature at state 3 is going to be equal to 100 degrees Fahrenheit. Okay, so what happens here in the condenser is it's going to be giving off heat out here. This is going to be Q out. And this is where, if you're dealing with a real air conditioning system, you're going to have outside air. This is that big unit outside of your house, that big unit. And let's say it's a hot day, it's 90 degrees Fahrenheit, and it's going to be coming out of here at some temperature greater than 90 degrees Fahrenheit, because all of that heat, we're trying to pull heat off that refrigerant. And so the air comes in at 90, it's going to leave 95, 93, something. It's going to leave a hotter temperature, depending on how fast we have usually have a fan that's sucking air in and blowing air out. That's what we have going on here. Now, after state 3, we go to state 4. We go through this expansion valve, and we're going to have, I just know that state 4 is going to be 62 degrees Fahrenheit. So that expansion valve is just like a throttle. It's just like a throttle. It's the same thing, valves and throttles. And it's going to be really, when it goes through that expansion valve, when we expand it, we're going to be dropping the temperature dramatically. and then we're going to go through an evaporator. And the evaporator, what we're going to do is that's going to be colder than the surroundings, and we're going to bring in heat from the surroundings in here. And so this is going to be Q in, and basically this is your room. So inside your room, let's just say your room was 75 degrees Fahrenheit, air was coming in, it goes through the evaporator, and it's going to come out at a temperature. Temperature is going to be less than 75 degrees Fahrenheit. So it's going to cool that air down. And they told us in the problem statement this Q in here is going to be equal to 600 BTUs per minute. And this is actually how a real air conditioning system is used. If you keep the air conditioner on in your car and you park it in the driveway or in your garage, and you hear that little that sound when you're stopping, that's the expansion valve. That's still the refrigerant going through your expansion valve after your system shuts down. Okay, so we want to figure out in this problem, we want to figure out what is the rate of heat transfer for the compressor. We want to figure out what is Q dot for the compressor. So here, it's a very important thing. We've been told that this compressor is not adiabatic. There is going to be heat transfer for this compressor, and that's what we want to find. Okay, so if that's our goal, it makes sense that we want to make our compressor to be our system. So that's what I'm going to choose first as our system and see what happens here. You might think that's a bad choice, but I'm going to go through it this way and find out what happens here. So the compressor is our system. Compressor is our CV, control volume. Okay, so I'm going to write this whole thing out. dE dt is equal to Q dot minus W dot plus the summation of my mass flow rate in, has my enthalpy in, my kinetic energy in, and my potential energy in, minus the summation of my mass flow rate exiting times my enthalpy exiting, kinetic energy exiting, and my potential energy exiting. We are going to assume that this air conditioning system is running. We're in the steady state portion of that, so this is going to go to 0. We are told to find the heat transfer for the compressor, so we can't get rid of that. We know that the compressor requires power. Okay? A compressor always requires power. A pump always requires power. A turbine always produces power. We know that that's the case. We're not giving any information about the kinetic or potential energy effects, so those go away. And so we're left with this. 0 is equal to Q dot minus W dot plus, there's only one flow going in and out of here, so there's mass flow rate times H1 minus Hn minus H exiting. We'll do it that way. And so our heat transfer Q dot is equal to W dot plus M dot times H exiting minus H entering, as I moved everything over to the other side of the equation. Okay, well, I know what the power is here because I was given it. It was 200 BTUs per minute. It's going to be negative 200 BTUs per minute because it's coming into our system. So this W dot should be negative 200 BTUs per minute. I do not know my mass flow rate. That's a problem. But I do know the enthalpy exiting. They gave it to me. It's at state 2. It's going to be equal to 130.0 BTUs per pound. And my enthalpy entering, which is state 1 up here, state 1 is a saturated vapor at 120 psi. And I know that I can go to my tables and I can find that value. So if I go to 120 psi, 120 psi, and I go to a saturated vapor, oh, just almost made a mistake. I'm looking at water. I have to remember this is a refrigerant. I have to remember it's refrigerant. It's an easy mistake to make, refrigerant, so it's R22. R22. Now we can look at it. R22 now is table A8. R22 at 120 psi, what a saturated vapor is going to be 109.88 is going to be our value for our enthalpy there. So now that we know that, we can put these two values in, minus 109.88 BTUs per pound. But we have one equation and we have two unknowns. So we have to go someplace else to find our information. Well, what I think that the best thing to do would be, is if we go back here to look at our control volume, is we got to make our control volume bigger. That's what I often say. We make our control volume bigger, or we have to analyze a different part of our system. Now, let me just say, what would happen if I made the system like this? If this was my system, I made it the whole thing, just like the last problem. Okay, how does this fundamentally changes our problem significantly? What is the biggest change that big control volume has made? Yes. It's a closed system now. Okay, now there's no mass crossing the boundary. This is a closed system. So look at this. If you look at this a little bit closer, remember when we drew this diagram? These diagrams here? That's a sexy looking one. That's really good. We had a hot reservoir, we had a cold reservoir, and we had this system going around here like this. See this little circle that we've drawn here? That is now what this system is. Okay, and here's where the hot and here's where the cold is coming in. Okay, so we're now, it's a bigger version or a more detailed version of this very simple diagram that we had here. So we don't want to deal with that because that's not going to help us with the mass flow rate at all. So what would you suggest that I choose as my control volume to help me solve this problem? Where is a control volume that will have the one unknown that I can solve for, and that unknown being the mass flow rate? Yes. Would you want to include state 3? You can. So what's your suggestion? Okay. So your suggestion is that we do this as a system. Okay. Here, I know what's coming in at 3. I can set that state. And I know what's going out at 2. I know that state. I know the heat transfer here at Qn coming in there. I know that. I'm still missing my mass flow rate at 1, or my mass flow rate coming through here, and I'm missing my heat transfer coming into the compressor. So I still have 2 unknowns there. Another suggestion. Yeah. Okay, we could, let's say if we just do the evaporator. If we just do the evaporator, now we still don't have the mass flow rate. Can we set the state at 4? We can. Because what's in front of 4? An expansion valve, which is another name for a throttle, which tells us that the enthalpy at 3 is the same as the enthalpy at 4, which is all we need. And can we set the state at 3? We can. And so this, because we know the heat transfer, we can use that as the control volume. That's one situation. Or you could make this your control volume. Forget about that throttle. Put it inside of there. Now we definitely know what's coming in at 3. We definitely know what's going out at 1. And we have one heat transfer coming in Qn that we know what's happening there. So either of these two control volumes would work. I don't care which one you use. They'll both give us the same answer. So let's now look at I'm just going to do the evaporator as my control volume. And so I'm going to write the first law, the E dt. is equal to Q dot minus W dot plus the summation of my mass flow rates in, enthalpy in, kinetic energy in, potential energy in, minus mass flow rate exiting, enthalpy exiting, kinetic energy exiting, potential energy exiting, and it's at steady state. It's a heat exchanger, so there's no power, and there's no kinetic or potential energy effects. And we're going to be left with 0 is equal to Q dot plus mass flow rate times H, let's do H4 minus H1, okay? Or, let's see here, Q dot would equal mass flow rate times H1 minus H4, and my mass flow rate is going to be equal to Q dot all over H1 minus H4. Okay, I just rattled off a whole bunch, wrote down a whole bunch of stuff, and I'm seeing you rapidly trying to catch up with me. Q dot, which was 600 BTUs per minute, is that positive or negative? Positive, it's going into the system. 600 BTUs per minute. H1, I know from a previous statement here, is going to be 109.88 BTUs per pound. H4 is the same as H3. So I'm going to look up H3, and I want to save a little bit of time here. And if I look up at H3, 225 psi, 100 degrees Fahrenheit, I'm going to find that at 225 psi, I saturate at 104.82. So that means I am a liquid. It's R22. Liquid approximation means that I look up the properties for this at the temperature I'm given. So I'm going to look up the properties for this state 3 so H3 is going to be HF at 100 degrees Fahrenheit. And that is going to be equal to 39.41 BTUs per pound. And because we have a throttle there, the enthalpy at 3 is going to be the same as the enthalpy at 4. And so we can write it down here as 39.41 BTUs per pound. And when we do this calculation, we find that the mass flow rate is going to give us 8.5 pounds per minute. That's the mass flow rate. That's the missing piece of information we needed to plug back in up here into our equation to find out what our heat transfer is. And once we plug that in, our answer is going to be that minus 29 BTUs per minute is what our answer, how much heat transfer we're going to have. So my question for you now is, if that's the answer, minus 29 BTUs per minute, is that compressor trying to heat up or trying to cool down? If I touch the compressor, do I feel it being hot or cold? I can ask the question two ways. Your hand feels hot? Why? You're right. You're right. Okay. Okay. The compressor has a Q of negative 29. That means it's what? Absorbing heat or giving off heat? Giving off heat. The compressor is trying to cool down by giving off 29 BTUs per minute of heat. Okay? So it's trying to cool down. If it was not doing it, now what happens is my hand goes on top of that. What happens is the heat from the compressor goes to my hand, and my hand feels hot. Oh, it's hot, it's hot, it's hot. So my hand feels hot while the compressor is trying to cool off. Alternatively, if I found that to be 29 BTUs per minute, that means it's taking in 29 BTUs per minute from the surroundings. And if I put my hand on it, my hand is the source for those BTUs, and it's trying to take the heat out of my hand, it would feel very, very cold. Okay, last thing. If I ask you here to find out what is the coefficient of performance of this air conditioner, you should be able to do this, because coefficient of performance is what do we want over what do we have to give. And that was given to you at the very first of this problem, because they said we wanted to have cooling, and we said there was 600 BTUs per minute of cooling, and we had to plug this thing in, and there was 200 BTUs per minute that we had to give, and so our coefficient of performance is just 3. Okay, so that's a very quick little add-on that we can put to this problem. Now we've investigated what a air conditioning system looks like, expanded plus that after that closed system. When you do your homework, when you do your practice for the exam, I want you to ask yourself the question, because we didn't do a very good job as a class as exam 1 of me knowing which direction the W's and the heats are. So you better damn believe that sometime I'm going to ask you about that again, okay? And there's not a better time than exam 2, not a better time than exam 3, not a better time than the final exam. There's not a better time than this whole damn class. So be ready to know what does Q dot negative and what Q dot positive is, what W dot negative and W dot positive. Make sure you can put the answer into words and explain to me what is actually happening. Okay, I'll let you go. Have a good rest of your day.